Well, how you doing, everyone, and welcome back. So glad you came back. You ready?
Absolutely.
Okay. Uh, so welcome back to the afternoon session. We'll begin with our highly anticipated panel with the topic, Open Source is Transforming AI and Hardware. Our moderator today is Dylan Patel, a well-known and highly regarded chief analyst at SemiAnalysis, an international semiconductor analysis firm with operations in the US, Singapore, and Taiwan. Ladies and gentlemen, please welcome Dylan Patel right here.
Thank you so much. Thank you so much for having me. I should get the least applause in this panel, first of all. So I really hope you can give Raja Kaduri a much larger round of applause. He was at Intel. He the world's fastest supercomputer. The world's fastest supercomputer, Aurora, was designed and architected by him, and it's just completed installation. Now he's got a self-startup, and don't know what he wants to say, but thank you, Raja. Andrew Feldman, CEO of Cerebras, founder of Cerebras, making wafer-scale computing, AI hardware startup, amazing stuff. Jim Keller doesn't need much of an introduction, I don't think. Everyone in this room knows who he is, so we'll go on to Horace. And Horace is at Meta. He's doing PyTorch, so we've got someone who's got software expertise, I will say. Everyone else here is a hardware head. And then lastly, we've got Charlie Chang, who's polyhedron, but he works a lot with Andes on their AI hardware. So round of applause for them, please. So the RISC-V community is amazing, and it's transforming everything. But the real most difficult thing about this community is actually how do we build the software and the tool chains on top, and especially for AI hardware, right? And so I'd like to maybe have a little bit of a discussion about what is the challenges. What are the challenges for bringing an AI hardware or AI stack to a brand new ISA, brand new, and what are the synergies you're getting from sort of using a CPU kind of compute? All three of these companies are creating AI hardware with CPU compute as sort of the base of it. So yeah, I'd like to hand it over to maybe Charlie could talk about the challenges, and we'll just pass it around.
So sure. So as a processor licensor, we see right now by now about a dozen AI architectures. There are customers, and this year alone there'll be about 6 new ones in the U.S. The thing about licensing business is that we get our money up front. But it's also sad that volume ramp up for most of our licensees have been very slow, if any. So I think that kind of outlines the struggle and the challenges of making the software come close, and hopefully one day be even better than what NVIDIA is offering today for machine learning. And I think that's the overarching statement, and I think that's what the company goal is. At Andes, we are part of the RISE, Project RISE, and we're going to be very active in that. But I think folks here probably have much better insight specifically about each of the incarnations of these problems.
I'll go next. I'll probably give more of like a software view. So from I think the PyTorch's perspective, the end users of these frameworks are not very sophisticated performance engineers typically, and so there's a certain programming models that a lot of the end users of AI models kind of generally expect, and it's kind of a model that NVIDIA has fit pretty well with kind of a large amount of flexibility in the execution and things like that a lot of more static AI accelerators often have a bit more trouble figuring out. So historically, this has kind of been, I think, a big obstacle to AI, to adoption of new hardware with AI hardware, with new AI hardware. But I do think that recently some of these things have kind of to become less of an issue with kind of the rise of these predominant foundation models with a lot more static design. So I do think in some sense that this has made the problem significantly easier.
I want to pause real quick. Horace, what do you think about there's a whole world of, hey, we're going to just insert your PyTorch code, let's compile it. And then there's a whole nother world where people want to tune very hard for the exact hardware they're using. What do you think about that? And then Jim, your company offers both, so I'd love to hear that after.
There's, or like, are you talking about like difference between just like, generic support versus support for like a single specific model? So I think one kind of challenge I've often seen with like very specific tuning for a single model is that you think of like typically AI hardware as there's just like a single, transformer model, a single architecture. But even within the single architecture, there's like a lot of variants of it, particularly in training, that may like often cause issues for like different, like between different models and different hardwares. So one example that comes to mind today is there were like recently an optimization in like the attention component called like multi-query attention, which significantly changes some memory properties of it. And this is something that, for example, like proprietary solutions like faster transformer that are like very hard tuned for single architectures, they take like a lot of time before these kinds of things can be adopted into these very specific solutions.
Yeah. So I think we have two different questions here. The first is, how are the software tools for building AI hardware? And like at TenStorrent, our initial idea was we're building an AI accelerator. There's a big multiplier, a big vector array, and we drive it with small RISC-V processors. And we have an interesting way of taking a big complicated program and building it across things. But at the lowest level when we started, I'd say like GCC, debug, LLVM, toolchain support, library support was somewhat weak, and we had to do a lot of work. We were somewhat unpleasantly surprised. We decided to move more of our development to LLVM. It had a bunch of issues. I talked to people like, oh, you need to know this guy and this guy to get this thing to do, and then she's going to do that, and it was pretty complicated. But that's like a really low-level software stack. Like, how do you build a real runtime environment where we can productively build extensions to like C++ and have compiler toolchain to do that? That's improved quite a bit. Last year we decided, we partnered with, we're building a high-end CPU now, and people want that to have server code and have more of a full solution as opposed to being an accelerator in an Intel box, like build an end-to-end solution. So we partnered with Bodhi Computing, which is an India startup that we're doing a little joint venture on software development. And again, it was interesting. Pretty quickly, we built a virtualization layer with an operating system on top of an emulator, multiple applications. A lot of the software pieces worked, but they work with more fussing around. They don't have the maturity. So something like RISE is going to be really great, where more people use the software, build it, and do just have to beat on software so everything works. And I think in the last couple of years, I used to tell people in 5 to 10 years, RISC-V is going to take over everything. The software rate of change is so fast that I don't think like another year or two from now we're going to be software limited on like quality of operating system stuff. Like it's going pretty good. I think there's a lot of details in the low level debug, runtime, tool chain, vectorization. Like it needs a bunch of work, but people are working on it. Everywhere I look, it's being worked. So your other question was at the high level. So the user wants to see a PyTorch program and run. So the world is loosely divided into two camps. There are people who want to write PyTorch and they think the software toolchain and hardware should make it go fast. And there's people to say, get that crap out of my way. They write reference models in PyTorch and then they hand code everything. I used to call this Andre Karpathy writes PyTorch and experiments with every model, and Scott Gray writes assembly language. And tools like Triton are specifically designed to get CUDA out of the way even, right? So there's the top-down approach and the bare metal approach. And this is, it's not a fight I'm in. Like we started with, we're gonna do the top-down. There's a bunch of things top-down compilers have difficulty with just because of, you take 10 simple operations and you put them together in a lot of different ways with lots of different sizes on hardware with a number of compilers, and you have a essentially unsolvable problem really fast. And it's not unique to AI, it's an HPC problem. HPC guy's been working on automatic compilers for 40 years, and they're making some progress, but it's slow. So you need a tool chain that lets you do metal. It's not an either or. And we belatedly said, oh shit, we should make a proper metal stack so customers can use it, not just us for testing. So we're going to release that this year. And I think it's going to maintain that way. And then there's combinations where part of it's high level, but then it calls low level libraries in metal, like the hybrid approach. It's essentially what NVIDIA does today. They don't really compile everything to PTX. They compile to libraries that are hand-coded in CUDA or PTX. And that's okay, that's normal.
So Andrew, your architecture is also, it's a sea of CPU cores at the end of the day, right? On a big wafer, so it's super cool. But how does that help you, make it more easy to program versus, of course NVIDIA has the entire software ecosystem today, but their sort of cores, right? Their SMs are much more restricted. So how do you think about that and as an advantage of sort of the sea of CPU cores?
I think there are two classes of problems. Jim just thoroughly crushed one of them. The other is there is no work that can be interestingly done on a single CPU, right? And so that immediately moves you into the world of distributed compute. And that itself is an entirely different world. I mean, we began with the world of compilers are hard. And compilers are particularly hard when the people who are writing the upper level language, whether it's PyTorch or TensorFlow, never once think about lowering the language because they're data scientists, they're not computer scientists. And so for the first 3 or 4 years in this, both PyTorch and TensorFlow were a disaster to lower. And that made it extraordinarily difficult to build a compiler. That's sort of one class of problems. Once you've compiled to a target, you then have another class of problems, which is you don't want to run it on one GPU or one of our machines or one of Jim's machines or one of Raj's future machines. You want to run it on 1,000. And that's a distributed compute problem. And that's an extremely difficult problem on top of the AI and on top of the compilation problem. And that's where having a big chip matters a great deal. If you have a really big chip, you can run strictly data parallel. You actually can use the easiest form of distributed compute. You never have to break up the problem. You never have to break the big matrices up, allocate them on lots of little GPUs or bigger CPUs. And so that was the thinking, that what's a parallel challenge in this world is how are you going to stick this giant collection of calculations on hundreds or thousands of GPUs. And that's the problem we went out to solve. I think most of us can build a core that's, the mapmul isn't that much faster at a given geometry, right? Whether it's some of the best in the world like Jim or our chief architect Gary, or the mapmuls are about the same performance. And so the question is, what else? Where else are you going to get performance? You're going to get it through your memory bandwidth. You're going to get it by not needing to move off chip, by these other techniques, by breaking up the problem differently. These are what's sort of interesting. And the other thing I'd point out is that what's described as the problem of taking PyTorch and lowering it is a training problem. The inference problem is really different and much simpler. And from that perspective, autoregressive inference is a really hard problem, much, much harder than all other forms of inference. But it's not hard because the PyTorch has to be lowered and it's complex. It's sort of static in that sense. And you'll see, in my view, a whole collection of very different solutions in silicon for autoregressive inference than standard GPUs or the traditional approaches. And a CPU might be a really good one for that, especially if you can eat through sparsity.
And so, Raja, I think you probably have the most experience with killing yourself against a software stack, right? I mean, GPU hardware at AMD, which is still behind NVIDIA in software, and then Intel. What are some of the challenges, and how can the RISC-V community maybe learn from it?
Nice guy, Dylan.
Killing myself or killed, right? Either way. How many people consider themselves software people in this audience? Okay. So about a dozen. hands up. It's a so. Let me tell you what I am up to actually, because that will, in some ways, answer the question, right? Like many hardware architects, my concept of software or like high-level software is C. Okay, it's like that no matter what they say, it's most people, right? It's basically like we still kind of high-level software is C. Okay, C runs, you got high-level thing. We see load every C statement I read, it translates to load, compute, store for me, right? Like I can understand. Some people throw in C++ loosely, like, oh my God, right? It's like A equals B means a million things, right? In C++, so not my favorite language at all, but like it stops at C. And with that abstraction, right, we build, at least kind of I'll talk for myself and the colleagues I know, we build like many generations of CPUs, GPUs and all, and like done a lot of stuff. And in the graphics world where I came from, right, that I understood what happens in a game engine, what happens in a game, what happens in a HPC program, which is kind of largely kind of C-like stuff. Even Fortran I consider a subset, restricted kind of C-like model. So I felt very uncomfortable over the last, I'd say, 3 to 4 years, where I felt I actually don't really understand what happens in the Python world. Okay, so like it seems like there are lots of people I work with. They all make statements. Oh, this is what Raji, you need to do this. You need to do this. You need to do this. But I felt like I lacked fundamental understanding of kind of what happens between Python and atoms, right? Like what we deal with on the hardware side. So that's one of the thing I wanted to kind of get out, and like just you cannot figure that out until you actually get your hands dirty and actually go kind of like Jim has this poster at one of his startups, Atomic Semi. It's called the scientific method. Okay, so the top half of the stuff is screwing around. Okay, it's more unparliamentary to actually say effing around. And the bottom part is find out, right? So it starts with like make an observation, do some research, make a hypothesis, okay? And then, run an experiment on your hypothesis, right? And like, then the circle completes to, okay, start maybe, your hypothesis was wrong, so come up with another hypothesis, right? So I'm in that hypothesis phase right now, so like so I'm screwing around. So anything I say is like say I'm just at this point like it's been a few months and being hands-on on all this stuff. So the short answer to his question is I feel all the people I talk to, even in the startup side, software side, like the guys, like he said, Jim said, Andre Karpathis of the world and Scott Grace. By the way, if you round to nearest, the Scott Grace of the world are 0%. Okay, that's what I found. They're 99. It's a big zero, right? 100% is Andre, class or in that category people. So that understanding, we really understand this stuff. So I read this statement in a data parallel programming handbook in 2005 timeframe. It was actually written in 1990s. It said, all successful parallel programming architectures have one thing in common. Their execution model, the hardware execution model, and the programming model match. Okay? And today, there is only one parallel programming model and execution model that match. Okay? And that is the $1 trillion successful companies. Nobody else's do. That's my short answer on why none of the other stuff, it's my hypothesis stage work.
Gonna start.
I was going to say, you should hear his long answer. It's really, really good.
So I'm curious, Horace, you're in PyTorch and you're far removed from anyone else here in terms of being not a hardware engineer, but today you can use PyTorch and it can compile to CUDA. right? Or you can use PyTorch and it can compile to an Intel CPU, right? And it goes through, you know, the whole stack. It gets lowered, you know, whether it goes through LLVM or MLIR or OpenAI Triton, you know, whatever it is, it can compile and it works and it runs. What are the biggest challenges to getting, you know, RISC-V there? What, you know, I know Meta is working on it, but you know, what's the challenges and what does this room need to do?
That's a good question. So I think there's like, at a high level, there's like a couple, I think of it as there's kind of like two stages of like optimizations that generally kind of need to be done with machine learning models. So I think, you know, from my perspective, you know, my programming model for a lot of these like machine learning models is like very much like array programming. It's like you have like a graph of operators. Each operator is like a, you know, a chunky, you know, matrix multiplication, or it's like a ReLU. It's something that operates on, you know, thousands or millions of elements at a time. And so you have kind of operations that kind of operate at this high level. You know, for example, things like operator fusion, or things like, you know, flash attention and kind of merging these together. And so these are kind of like one level optimizations, and these are kinds of things that like PyTorch can kind of do like generically, or, you know, other ML compilers kind of do generically for the hardware. But on the other hand, you have like the, you know, once you've decided your like, you know, work grouping thing, like what is like a single work, like single operator on the hardware, you then need to figure out how to actually like turn this into something that runs efficiently on the actual hardware. And so today, for example, we rely heavily on things like OpenAI Triton to kind of do this mapping for us. So I think from my perspective, I think the easiest thing to do would be if there was like a good RISC-V backend for Triton. That would definitely make our problem much easier. Although I do think one kind of common problem we see is that the Triton programming model may not map nicely to many kinds of hardware.
Yeah, you made me think of two things. So one is, like, we built a whole world of software, like for 50 years or something, where the number of processors was 1, right? And everything, the operating, like, get this, like, I'm not kidding. Today on a computer, a processor runs the operating system, it schedules other threads, and then they run on the same processor. I'm not kidding. And that's even though you got 100 cores, like, you know, they're all taking turns doing crazy shit, right? If we had started with Andrew's computer where the minimum number was 10,000, right? Like, that would have been a good number, right? And we would have built completely different kinds of software, right? And we're going through the transition because millions of computer people think that programs run in order on one processor, right? So that's a funny thing. But so the default for AI is like, the minimum number should be 10,000. Like, nobody should have less than 10,000 cores. And we agree, that's probably true, right? Now, the irony of AI is, you think, oh, I'm going to take this matrix multiply and put it across a lot of cores. And what's matrix multiply? It's an all-to-all calculation. You take every element of a row and every element of a column and multiply them together and then sum it. So it's like what we wanted is AI to look like, you know, finite element analysis, where you have little elements do their local work and communicate with each other. But that's not how AI works. Like, you think of AI, it's like, oh, yeah, you know, the fused operator, and you just mentioned 4 element operators, which are the only easy ones to do, right? Like, but that's as a hardware person, right? So we have this kind of funny world where the number of processors by default is large. And the reason they're large is because if you make one processor really big, it'll be inefficiently utilized, compiling for it sucks. The power trade-off, you don't want every bit to go across the whole chip on the SRAM, so you want local processing, so you have to break it into small pieces, right? But then all your operations are all-to-all, which is the opposite of what you want. Again, everything's wrong. And, you know, solving this problem is hard. And as Raj has said, the fundamental constructs of what the hardware is trying to do and what Horace is trying to do in software don't look anything like each other. So now we're trying to build a bridge between the two worlds, and it's curious, but it's also historic fact because of how processor and languages evolved. Because they spent a lot of time one program on one processor, and that's not the world we live in, and nobody's really built a new framework that's tens of thousands of processors, fundamental things are all-to-all operators, which is, you know, it's just weird how that worked out.
And you know, so far we've talked about a lot of the challenges, but you know, the real you know point here is what is open source doing to help everyone, right? I mean, you know, you've open sourced models, you've open sourced floating point units, you know, you open source so much of PyTorch, right? And you've contributed a lot, you know, how is open source helping, you know, take down the $1 trillion gorilla, right? You know, anyone can answer.
I'll start, right? So for more than maybe 20 years, right, many architects I know had really good opinions on ideas on how to make this kind of, you know, 10,000, you know, kind of parallel computer easier to program. But the core for that is really that starts with the CPU architecture. Okay, so it's not the other things, because other things are easy to control once you can actually control the CPU architecture. But we were stuck with, where I was stuck with building blocks that cannot be changed, right? Adding an extension or modifying x86, I'll be burnt alive, okay, if I propose that. And ARM ecosystem, again, has its set of problems. What I saw in the past 6 months in the RISC-V open ecosystem, it just blew my mind away, right? Is that, oh my God, all the things that we've been dreaming, we could actually go do. Nobody is going to say no, okay? And I see people in the ecosystem doing some really fantastic, interesting things, including the, you know, the tensor and core and how they arrange the RISC-V processors and several other efforts, right? So, you know, AI computing or this new form of computing cannot happen if you treat the CPU as a black box, okay? You cannot address real Python programmers' needs if you treat a CPU as a black box. And if you think AI is this offload mechanism and this stuff and all, my view, you're on the wrong path, okay? You're already on the wrong path because you aren't starting with the programmer first approach.
At Cerebras, we think to do AI, you need three things. And I think you've got on the panel people who are doing each of those. You need compute, you need big data, and you need a model, right? And I think there are different ways to attack all of those with open source. Jim's attacking it with open source on the compute side. We've open sourced 7 GPT models. We just open sourced the largest clean data set. And I think together what you're seeing is an ecosystem that's attacking the end-to-end problem of how you do AI. You need compute, data, and models, and none of us can do them all in the open source community. And that's why there's an ecosystem. You're going to see this from different strata are going to put forward their preferred part. And together, you're going to get a vibrant ecosystem. And I think that's what you're seeing right now.
Yeah, yeah. I was like, when we started doing, we're about to tape out a part, and when we started it, I went to ARM because I needed some higher performance cores, and I thought their compilers are rock solid. My path to tool chains running Linux locally on the processors, a bunch of nice things, but we absolutely needed a couple of extensions. You know, we have 16 and 8-bit and 4-bit floating point. There's some weirdo details about how accumulators work. Yep. It's 20 lines of RTL, to be honest. So I talked to ARM, and they said, no way. It's like, what do you mean, no way? Like, we're friends. Like, we've worked together for 20 years. And they're like, yeah, no, we're controlling this, and we're going to do it when we're ready. It's like AI when you're ready. Like, this should have been in there 2 years ago. This is not like 2 years from now. And so we're like, well, we can't build the product we want. I'm not going to ship AI data to the ARM and spend 20 cycles converting the 8-bit flow to my format to the 16 flow to their format. It's stupid. It's super easy. I called Sci-Fi, and they said, sure, we'll put it in next week. Like, it was literally like that. Like, wait, kudos to those guys. That was great. And it was reliable. In our little baby, we call them baby REST set driver AI engine, we had to add semaphores and a few other things. But then this is where you get into the little mystery of open source needs some commonality so you can leverage and share stuff while giving you room to fuck around so you can do experiments and find something out, right?
Otherwise, it's a mess, right? You know,
It's a mess.
Otherwise, it's a mess.
Yeah. So what we did is our processor runs the standard tool chains and stuff, but we added extensions for instructions, data types, and then some semaphores so the processors can coordinate, essentially register to register. One guy can say, I'm done. The next one, you know, goes the next cycle without a lock. And we have a few extensions, but it works with the standard tool chain. So this is like, but the Roger said, it can't be a black box. You got to make the changes you want. And the cool thing about innovation is the faster you innovate. If I have to innovate by asking ARM for permission to get a core in 5 years so I can do an experiment, that experiment loop is terrible, right? And RISC-V has the opportunity to have a fast loop. And we saw this happen in software. I remember years ago, we had a printer driver bug on NT. And we reported to Microsoft, and they said, yeah, we know. And a year later, we got an update on NT, and they hadn't fixed it. We had already switched all our CAD servers to Linux, which also had random bugs, and we called our buddies, and they sent us patches, and everything worked. Right? The iteration loop was 10x. Like, and that's the innovation key.
And that's how you beat the big guy, right? I mean, you don't beat him in one big bite. You beat him with hundreds of those little iterations that are vastly faster.
One of the things that you know, someone who many in this people in this room will know is John Masters, one of the biggest evangelicists for ARM. You know, one of the big criticisms he has for this RISC-V open source effort is there's no, you know, quote unquote adults in the room. Because people are innovating in 100 different paths. So how do you bring commonality between what Andy's is doing on RISC-V AI and what Tenstorn is doing on RISC-V AI, and you know whoever else is.
Yeah. Here's the best quote: is Andy Grove, "Let chaos reign, and then rain chaos in."
Yeah.
So what people want to do is call the shot before the plays and experiments are made. That's wrong. He's wrong. That's why he's.
By the way, same could be said of all AI, so it's good. Let kids play with kids, okay?
The only people who call for
We don't
adult
need any adults in the room.
The only people who call for adult supervision are those who think they're adults. Right. I mean, kids are never like, you know, well, what we really need here while we're playing with our friends are some adults to screw this shit up. Right. I mean, that's not it. I think there is truth that during a Cambrian explosion of innovation, there are a lot of cul-de-sacs. There are a lot of innovation cul-de-sacs. There are a lot of dead ends. There's a lot of work that gets set aside as not the path forward. I think that's the price you pay for vast innovation. Don't you think?
Yeah.
Otherwise, you're on one path, and sometimes that screws up too, and then you're only on one path.
Yeah, I'd you know, like to say one thing. Here we are in 2023, and yeah, you could kind of, you know, rank my statement here in 2027 or 2028. PC era was x86, mobile era was ARM, AI era is RISC-V. Okay, so we'll see if that, you know, I think give me till 27, 28. Okay.
Yeah, I think we agree with you on that. I think just a lot of innovation.
It's a surprise, Charlie. No. Does anybody else?
I'm very objective.
Does anybody else who's
Anybody
in
else
RISC-V
agree on that?
disagree with this statement?
But so one thing I see that allow the kids to play and still connect as quickly and directly to, you know, Horse PyTorch is emerging, and I'll just tell a funny story. We all just came back from a Lunar New Year in February. Our largest customer said, we need to have a meeting. I said, great. Half the engineers are still on vacation because they've been locked up in Taiwan for 3 years because Taiwan had quarantine if you travel abroad. So half the people are not there. So the large customer says, we need LLVM 16 yesterday. We said, what do you mean? You've been on LLVM 13 for forever. So unbeknownst to them, you know, LLVM, which is an open source compiler, has made so much progress between 15 and 16 that they need it yesterday. And that is, I think that's a watershed event for not just ML and not just RISC-V, but for the world, because for the very first time, what HPC people have been working on for the last 40 years and couldn't get it done, which is auto-vectorization, now looks very clean and very, very good. And it's caught our customers by surprise, and now everything is, is like every conversation I have with customer, the first thing is about LLVM. And it replicates to a lot. And I see, so, we say we're going to let the kids play. Well, one way to let the kids play with all their crazy RISC-V extension is to make them all invisible from Horse so that when Horse compiles, right, those are largely just instructions. And so how to make it so that LLVM compiler can see all that with just languages is the thing that we've been doing a lot. And I definitely see a path where one day there is PyTorch or hopefully another one that's even better, right, Horst? You're working on another one, right? Okay, so something even better than PyTorch, and it goes straight to some open source compiler, maybe LLVM 25 or something, and it goes straight to everyone's hardware. We have to worry about memory latency. We have to worry about mass amount of data that's coming in and out. But at least from programming and perspective, it will all be a lot easier than what, the monster gorilla is working on.
Maybe Horace can comment on, will there be human-written programming languages 5 years from now, Horace?
Or like human? What do you mean?
Like human-written, people writing programs versus it's all
He's asking about human.
generated
Are there going to
code,
be
like
human?
in this stuff, right?
Or will like large language models write all of it?
Write all
You're
the
looking
code
for
like
workhorse? Is that-
Who knows? Who knows? I mean, I think if language models are coming for programming, I think they'll also come from our hardware too.
Certainly place and route.
The interesting thing about large language models, right, is that you need the data to train. And one sort of idea that I've had, and I'm sure many others have had, is why can't we, people are generating Python, people are generating C, people are generating all sorts of code with large language models today, but no one can generate system Verilog, right? And it is this archaic thing that I'm sure many people in this room work with a lot. You think, how do you think large language models could change this, right? AI and all these sorts of things. And there's no, open sourced system Verilog, really, a little bit.
I know some people working on that. Don't worry. System Verilog's not rocket science.
We have a whole series of projects with non-English language chat. And one of the things that's really interesting is even for languages that you think there are a lot of people, there aren't enough tokens, like Spanish, right? I mean, how do you get 1.5 trillion tokens? Well, you take the whole English language internet, and you don't scrub it at all. That's how you get 1.5 trillion tokens. You can't get that in Spanish. You can't get it in French or Portuguese. You can't get it in Arabic. You can't get it in any other language. Now, the Chinese work really hard at translating the English language internet into Chinese so they can train Chinese language models. But these models consume vast amounts of data, and I hope Jim's friends, because we use System Verilog, I mean, I hope they have enough data, or they have really good synthetic data, or they have all sorts of other techniques to generate it, because otherwise we're going to be stuck in this world of English only for these large language models. It's a real challenge.
Yeah, maybe we'll just write our future hardware descriptions in English, and then we'll bypass that little problem.
That would be nice.
My goal changed from Python to English now.
So we've talked a lot about like the CPU core, the compiler, but what about, and this is not necessarily RISC-V, but memory, managing communications between cores. Everyone's hardware looks very different in terms of core-to-core latency and the size of the core. And is this just something that has to be programmed individually for every single accelerator, because every single accelerator is going to look different on that? I mean, NVLink latency versus NVIDIA's, SM to SM latency is very different than what, Tenstorrent is doing, which is very different than what Cerebras is doing, which is very different than what, Meta's doing, with their hardware. Yeah, how about?
Well, I have a funny opinion about this. So I was at Digital Equipment when Digital owned, networking with DECnet Phase 4, and TCP/IP was coming, and that was the no adults in the room networking stack, right? And by the time the adults at Digital produced DECnet Phase 5, they were dead, right, essentially, and TCP/IP worked. But one of the things, the constructs in it is a really well-architected set of abstraction layers, right? And then periodically, somebody invents, I remember the first InfiniBand spec, and it was like way faster than Ethernet because they cut through the abstraction stacks, wrote a 1,300-page spec of cross products that they never solved, and they didn't really get it until they simplified it radically. And they still kind of blur some layers to short-circuit it. But fundamentally, network stacks work really well when the abstraction layers are clear, like what's layer 1, 2, 3, 4, 5, 6. So at the end of the day, Ethernet always wins, right? Partly because they're pretty rigorous about the abstraction stack. And, when hardware guys have to scale and be interoperable and stuff, you need that kind of stuff. And which is one reason we picked Ethernet to start, because we use Ethernet as a layer 2 transport, and we just packetize stuff and ship it around. And the PHYs work, the Macs work, the cables work. It's all pretty good, and the latency over PCI Express is 20 nanoseconds. Who cares?
And it's been one of the great multi-vendor successes, right? If you look at our industry over the past 30 years, the rise of Ethernet and its ability to support different switch vendors, different host vendors has been extraordinary.
On the big scale problem, right? I think we're still in get it to work mode, most of the industry, right? Then get it to optimize the last 10%, last 20%. So some of the real kind of NVLink level problems, if you leave NVIDIA out of the equation, they are not the first order problems on why the industry isn't taking more market share from NVIDIA yet, right? They will be, right? Second order problems, third order problems, but you got to get the basic stuff working and kind of, be within 2x on every workload.
Yeah.
You get a lot of money, there, and then you can get to the last 5%, 10%, 20%.
Dylan, do you want to take some questions? Any questions before we dismiss the panel? Question?
Thank you. So how do you see chiplets affecting processor architectures moving forward?
Well, we want to make the computer systems bigger, right? That's a dynamic, right? And wafer scale, as Andrew can tell you, is both super cool and super hard, right? And then for years, people at various degrees have put multiple chips in a package. The thing that's kind of revived the chiplet thing is really fast die-to-die connectors, some standardization like UCIe, the ability to do multiple chips in an organic package as opposed to silicon interposer. So,
And the difference in cadence between SerDes and the rest of your chips.
yeah. So like I build a chip and I realize, I bought $10 million of IP I didn't really care to change. It would have been fine in the previous node, right? And so, but to do that, you have to have a low enough power die-to-die thing so you can say, this is a memory controller chip, this is a network accelerator, CPU and AI, and the specs of the new stuff is pretty good. And in terms of innovation, it could be that suddenly you could go build an AI accelerator company and only have to build an AI chip because you can get a CPU chip and you can get a memory controller and you can get an NPU. 2 years ago, to build an accelerator, you had to do everything. And, even if it was only to buy it and just relay it out on your chip. So there's an opportunity, which I'm excited about it. We believe in it. We're betting on it. But it's because of a number of kind of, let's see, evolutions of things that came together to like enable this. And we'll see how it goes.
Do you see like you're saying the CPU, what about the L2 cache, the L3 cache?
they're way too small. Like, so the minimum chiplet size is going to be 510 millimeters, and L2 cache is 0.2 millimeters. It's too small. Like, so you'll integrate the stuff that matters. You have to aggregate enough. And the nice thing is, well, the wild thing is some of the chiplets you can now just do as shuttles. So you can do a shuttle for your tape out, and that could be a production silicon if it's the right thing. So there's a bunch of enablers to this, which I think are going to be big. But those kind of components are too small. They got to be big. Think,
SerDes.
yeah, SerDes. A big block of SerDes with a Mac, a controller, a cache maybe. You're at 10, 15 square millimeters, depending on your port count and accelerator. But then that becomes a building block, which is pretty exciting.
This question is for Andrew and Jim. You both brought up this concept of innovation is gradual, which is the core ingredient to success. What can be done to, obviously this room agrees and we all know that this is gradual, but what can be done at this point to grow this innovation mindset in the community?
I think we don't use RISC-V, but we are huge advocates for it. I think a whole series of things happened to stagnate our industry. Tape outs became too expensive, so graduate students in EE stopped doing them. As a result, they only worked on FPGAs, which are a poor man's piece of hardware for sure. And as a result, if you wanted to build something, you were doing it in software and CS. And I think for those of us who love hardware, that was a disaster over the last 20 years. And you'd see EEs who'd never taped that apart. You get out of a top school and you've done some work on an FPGA. I think things like RISC-V put back into the realm of our graduate students and even our undergrads the ability to make things. And I think for those of us who love hardware, some of the greatest minutes of your life are when your hardware comes up, right? This is when your idea breathes. And I'm sure Jim and his team are in the lab, and Raj, you're in the lab, and when that piece of silicon comes back from TSMC and all your guys are there, and you got it on a board and it comes up, that's a magic minute. And if you steal that from your graduate students, and if you take that away from your postdocs because it's too expensive to do a chip, you rob them of one of the truly marvelous things of watching your idea breathe. And so I think that's one part that this can really help with. I'll let the others comment on this.
That's why jealous of software guys, because they have those magical moments every day, right?
Question over here.
Yeah, I just want to say, it's in the interest of incumbent monopoly players for things to be expensive and proprietary, right? So RISC-V is open source, which lets you do one kind of experiment. Chiplets is an example of how do we lower the incremental cost. Shuttles was really important. Community shuttles, I know students, like group of students, like 100 different designs on a shuttle that they split the shuttle cost. So that lets you iterate there. But, innovation, like the overall curve is slow. The number of innovations under the curve is really high, and it tends to move around. I think we're doing pretty good. Like,
it can't be that Jim and I need to raise money, right? I mean, that's bad. Between us, we have 70 years of doing this, and so it's easier for us to raise money and raise big piles. That's bad for innovation, right? We need to be able to innovate with $2 million of risk capital and a 3-person team like they do in software. And so I think that's a really important element too.
Let's take the question over here. Go ahead.
Yeah, sort of related actually. How do you view the friction of software development for pre-silicon hardware, right? Emulators are expensive, hard to get access to, hard to operate.
yeah, the tools and stuff have gotten better. So we brought up about 6 months ago our high-end processor. We booted Linux on it. Some of it's methodology, which I've talked a little bit about. Like we designed the processor clean slate, really modular. We built a reference model, the microarchitecture performance model, RTL, to be modular. We can boot any unit of the thing, so we made the problem smaller. Divide and conquer is a beautiful thing. The number of interfaces in our chip is relatively low. We don't send a bundle of 500 spaghetti wires from the execution unit to the load store unit. That's a defined interface. So some of this is like software methodology for hardware guys. Like, we're slow to learn, but this is a powerful thing. The emulators aren't terrible, to be honest. Like, the modern FPGA emulators, you can get a really big processor in a pretty small box. It's not $1,000, but it's not $1 million anymore. We use $1 million emulators for really big, complicated things when it's worth it. But we can get pretty far with modular design on CPUs and then small emulators. So I don't feel emulation constrained.
And there are actually.
But that's a strategy. Don't take a big, ugly design to a Palladium and then whine about $1 million because you blew it 2 years ago in your planning stage.
Yeah, I think there are, just in the interest of open source, there are actually a lot of open source software models and software technologies that you can use to bring up hardware. So a lot of our licensees do that, and I see them being very effective.
Well, let's,
One more right there.
right here? Okay.
Thanks panel discussion. You guys mentioned a very important concept called the program execution model, which can improve the software productivity great. And I know I have to mention one important architecture called the data flow architecture. So I want to the panel comment on whether data flow can be revived to support, especially Jim mentioned, 10,000 processor. Thank you.
Data flow architecture like Arvind from MIT in the 80s? Is that what you're referring to? We're a data flow architecture. I think maybe Jim and Raja will agree with me that most of what we do, IBM invented in the 60s, and we're just coming back around to it when we stumble into a workload that's good for it. I think data flow has some really terrible characteristics for many workloads, and it has some really interesting characteristics for other workloads. And I think a workload like AI is really well suited for a data flow architecture. I think the essence of data flow is not going to get information, but having it arrive at your doorstep with at your core with what it needs is very much in line with our view of the right way to execute an AI workload. But I think these things have unfortunate sort of religious connotations, right? There are a lot of really good ways to skin a cat, really good ways. And this one worked with our way of thinking. It's worked with some others, but it need not work with Jim's way or with Raja's way. They're going to make some other trade-offs, and they're going to think about the problem a little differently, and but both can do or all can do it extremely well. I think that's the fun part about computer architecture.
My observation is the fundamental issue is we taught ourselves and all the programmers what I call the program flow. Okay, like, that it's a set of instructions, commands. And yeah, there is data accesses and all. It's like fundamentally we don't teach data flow, right? We do not teach data flow. So while it makes intuitive sense after we look at a problem, and only if they actually just say, like, the entire thing, and there are no good data flow programming models that I can just, weed off the stuff. So I think that is the problem. It's not that the idea is bad. It is that, like, it's kind of like language. It's like, there may be extreme 100 times more efficient language than English, but we know English, right? This stuff. So it is.
So, Raj and I famously strongly disagree about a couple things. So I didn't know this was one of them. It's good to know. So humans have a really weird property. Like, we have a distributed brain with 10 billion neurons, supposedly, that talk to each other at a couple hundred hertz or whatever, right? Which looks like a parallel computer or something, but we think in linear narrative, and even weirder, our thoughts right now are just right now, And our current thought has a past, what we thought, and a future, but we execute at the program counter. So we are be here now machines, right? And program models do this. You write code, but when you're looking at code, you really think it's executing there, and the stuff before where you're looking is done already, and the stuff after isn't done.
You can tell Jim is a CPU guy.
I'm a CPU guy, so I've spent
CPU guy, brain is a CPU.
I've
For a GPU
spent
guy, the
40
brain is-
years. So the weird thing, like a processor is pipelined, which is fundamentally a data flow architecture. So when a program is running, one of the things you learn when you go pipelining is there's something different happening in every stage. Humans do not think that way, at least very few, right? So there's a natural problem of data flow because human thinking translates to a C program beautifully, struggles to a functional language, right? And pipeline is something you spend your life doing. And the problem with system Verilog, by the way, isn't system Verilog to write a program that runs like a C program, it's pipelining. And pipelining is hard.
All the time goes.
And then as soon as you start the pipeline, you find, guess what? The pipeline runs as slow as the slowest clock stage in it. So now you have to do pipeline balancing and staging and data flow and pipe stage interaction and pipeline reset. And I spent 4 years doing it, and I suck at it. I'm just better than almost everybody else, right? And that's because it's fundamentally crazy.
All right, well, let's wrap it up and give our panel a big hand. And thank you, Dylan Patel. Thank you so much. We're gonna bring up our next speaker.